Okay, so in the previous video, I showed you that the interval between two events uh, is invariant with respect to the choice of um, different inertial frames. And now I would like to show you how to obtain the Lorentz transformation um, from such treatment automatically, more or less. Okay, I hope you could see it. If you haven't watched the previous video, watch it because we'll use the results from it. So in the previous video, we have obtained these two equations in the radar coordinates of Alice and Bob, simply from the geometry. And by multiplying them together, we got the conservation of the interval, the invariance of the interval between these two events. Now I'll show you how to obtain the Lorentz transformation. It's basically these equations. We just write them down in standard coordinates, right? It will be T B minus, minus XB over C equals K TA minus XA over C. And here we have TB plus XB over C equals to, A. Game times TB plus XB over C. Now we just need to solve this equation for TB and XB. So if we add them up, multiply by K and add them together, we get 2K TB equals to TA plus XA over C minus K squared TA minus XA over C. So in other words, TB equals oh, sorry, I made a mistake. There's plus here. Equals K plus K inverse over 2 TA minus K inverse over 2 XA over C, right? I guess it's correct. Now, again, same for XB. XB over C. By the same calculation, you'll get K minus K inverse TA plus K inverse over 2 xa over c. So if you write it in a matrix form, yeah, I don't know whether you already recognize the Lorentz transformation or not. Indeed, here they are. We only need to express the k factor in terms of familiar variables, the velocity. How we could do it? So let's look again at this setup with Alice and Bob and see how Alice could measure the speed of Bob using for radar. So they met at point 0, 0, right? And then they communicate using light rays. So she emits a light ray some moment. Then let's say the light ray hits Bob at position A, X and moment T. And then it reflects and returns back to Alice like this. So let's say we know that this moment we call EA, right? And this moment we call RA. From our previous treatment, we know that this distance is K times EA, right? And we know that this distance, RA, is K times this. So it's K squared times EA. And now we need to remember the relation between RAEA and T and X, TAXA. TA is just half a sum of RA plus EA, and XA just C over 2 RA minus EA. Substituting this result, we are getting K squared plus 1 EA C over 2 K squared minus 1 EA. Now, for the velocity of Bob measured by Alice, we're then getting XA divided by TA. We have C times K squared minus 1 divided by K squared plus 1. Now let's let's solve for K. So if we introduce V over C equals to beta, a standard notation, we have 1 plus K squared times beta equals K squared minus 1 So mm, what do we have? T squared times 1 minus beta is equal to 1 plus beta. So k is equal to square root of 1 plus beta divided by 1 minus beta, which is exactly the standard answer for the Doppler effect. So yeah, it's not easy, not that hard to show that this is equal to 1 plus beta. Minus beta square, which is equal to gamma. And this is equal to beta times beta square. So gamma times beta. And therefore, our Lorentz transformations, they take standard form. Okay, so we are done now. We derived both the conservation of interval and the Lorentz transformations simultaneously from this radar coordinate trick. The last comment which I would like to make, oh no, sorry, is that that's not the only way to derive the Lorentz transformations. This is a more or less a standard derivation. It relies on absoluteness of the speed of light. Um, the speed of light is the same in all inertial reference frame, which is more or less is based on the result of the Michelson-Morley experiment. But there is a alternative way. Show you. Here's the paper about it. I'm not sure I read exactly this version, but I'm familiar with this kind of setup. So here we don't actually rely on any light behavior at all. This derivation only assumes homogeneity and isotropy of spacetime and relativity principle, that all laws of nature are the same in all inertial frames. And from this assumption, those people derive the most general form of coordinate transformation between inertial frames, which include both Einsteinian and Galilean results. So the answer depends on some parameter. And if this parameter is taken to infinity, you naturally obtain the Galilean result. And this parameter has the meaning of maximal relative speed. And we know from other experiments that this maximum relative speed is not equal to infinity, that it is actually finite. For example, whenever we accelerate our, protons on LHC, we pump as much energy into them as we can, and we clearly see that no matter how fast they are, the velocity could not exceed certain limit which coincide with the speed of light. Same for cosmic rays. In cosmic rays, we have particles which move even faster than at the LHC. They move at sometimes at some ridiculous speed, and uh, the source of which particles sometimes is even unknown. Um, but the speed is still, yeah, never faster than the speed of light. It's as close to it as it gets. Uh, but no matter how high the energies are, they're still bounded by this limit. Um, and that's allow us to make the choice here between Galilean and Einsteinian transformations in the end. So if you want, I could go over this derivation as well, but it's relatively straightforward, so I don't see the need to do it right now. And certainly if we do it, I'll make a separate video about it. So that's all for today. I hope you enjoyed this simple derivation with radar coordinates. Share it with your friends and so on. Goodbye.